we go.
There we go. So that has to be on. Okay, yesterday we started to learn about the sine function and the cosine function. And the goal here is to be able to do a decent estimate of what the sine or the cosine or eventually the tangent and whatnot of any value is. Okay? Because you have to have this intuitive gut as to whether or not the answer is what it is. Okay? So for example, if I said to you, based upon what we learned yesterday, if I said, what is the sine of 87 degrees? Give me an answer that is within 1/10 of an answer, within 1/10. Right about 0.9. Okay. Now, why is 0.9 a good guess? Well, it's based upon our circle that is our unit circle, and we look at where this is. Yesterday we established a couple of facts. One fact is that every single coordinate, this is like so amazing, every single coordinate that's on the circle actually represents the cosine of theta and sine of theta for whatever that theta value is. So this is the connection. This is the big connection. That this is your starting point. So this is 0 degrees, and we're pointing just perfectly to the right. And then 87 degrees, yeah, it's like about right here. Okay? So we're saying that this angle measure right here is theta. It's 87 degrees. And we learned by the right triangle trig that the cosine is the x-coordinate and the sine of that angle is the y-coordinate. That sound familiar? That's what we said yesterday. Therefore, all you have to do is find where the y or the x is. This one here is super close on the y to the unit circle, which we knew with the radius is 1. So the answer has got to be around there. It's probably like 0.99 or something. Okay, test it out. Punch it in there. See what you get. .9986. Okay, so it's way up near the top. Okay, so if I said, all right, what is the cosine of 87 degrees? And I said, give me a rough estimate for that. If you get 0, you're probably going to be within 1/10. So 0.1, somewhere between 0 and 0.1, right? Why? And that's because if you drop down the x-coordinate here, okay, for where that is, it's going to be somewhere really close to, 0.0 something. What is it? 0.0532. Okay, so that's it. So anytime that you're thinking about the sines or the cosine, that's the deal. Okay. Now, your calculator is in degree mode right now. I want you to switch it to radian mode. Because guess what? On the AP calculus test, we don't use any degrees. We only use radians. Okay? Yeah. All right? So now we have to figure out this whole radian thing. All right? So what is the connection between degrees and radians? And how does that work when it comes to this whole unit circle thing? Yes, Tim. So 2 pi, this is what I'm hearing, 2 pi what? 2 pi something is equal to 360 degrees. 2 pi radians is what I'm hearing. Okay, 2 pi radians. Did you ever hear of that? 2 pi radians? What do you got? Oh, nothing. Oh, okay. That was out there. So 2 pi, I've heard that too. 2 pi radians is equal to 360 degrees. What does that mean? What is a radian anyway? Xander? Yeah. A radian means Xander has to go to the bathroom. Not put that as an answer on the test. Okay, say that one more time really loud. Everybody listen.
A unit of angle equal to an angle at the center of a circle whose arc is equal in length to the radius. That's how you explain.
Whose arc is equal to the radius. Whose arc is equal to the radius. Okay. What does that mean? All right, watch this. Yeah. Okay, so let's figure this thing out. Okay?
I don't understand. Yeah, teach us that.
The only problem is I can't draw a line to save my life.
We'll make a video.
Yes, a tutorial. Okay, so here's what I heard. We established that this is 1 unit. Okay, that's what we said. And then what they're saying here is that the arc, a radian, 1 radian, is the arc length, which is equal to the radius of the circle. Okay, so here's what we're going to do. See this mark right here? I'm going to peel that off. Okay? Ready? This part right here is this radius, this dark part. I'm going to peel that off. Okay? And so, ready? There it is. Okay. So, here's my radius, okay? All right, this radius is equal to 1 radian. 1, okay? It's equal to 1 radian. Okay, so what I'm going to do is now I'm going to make it be an arc, okay, on the circle, on the unit circle. So I'm going to put the one end down here, and then I'm just going to drag the rest of it around here and see where it lands, okay? So as I do that, okay, put the one here, stick it on, grab the bottom, put it on right there. Okay. I slap the radius on the circle. See that? This is how long 1 radian is. That's how long 1 radian is. Okay? Now, 1 radian is that far along. I wonder how far it is all the way around the whole circle. If that's how far it is, I wonder how many of those I can fit on the circle. A little over 6? Maybe 6.28? Okay, so I'm going to go 1, 2, 3, 4, 5, 6. Yep, I think you're about right. Okay, but I need mathematical proof. How many can I actually fit in there? And I need I need a mathematical reason why the answer is a little over 6. Yes?
The circumference of the circle is diameter pi.
Okay, so somewhere along the line we learned the definition of a circle, of a circumference of a circle. Pi times diameter, or you learned it as 2 pi r. Okay, same formula, different letters. And so the circumference of this circle is how much? It's pi times 2, right? Or it's equal to 2 pi. Okay? So it's equal to 2 pi if we go all the way around, which we know is somewhere around 6.28. Okay? So what are the units? If I said that this is 1 radian, which is at the length, 1 radian in length, that means that I have 2 pi radians if I go all the way around the circle. Okay? So if I go all the way around the circle, that means I have 2 pi radians if I go once all the way around the circle. Make sense? So what this means is, and how many cross-country runners do we have? Anybody? Okay. So imagine this. Imagine somebody designs a course, and it's a circular course. Perfect circle. Okay? And then you start here. Okay? And the radius of the circle is 1. Okay? Let's make it 1 mile. If you go all the way around, how many miles do you run? 6.28. Okay, so that's the deal here. If it's 1K, then it's a 6.28K distance. Okay, so now we know it's all the way around. We're going a distance of 2 pi. But I wonder if we don't go all the way around. Okay, instead of going all the way around, so I'm starting here. If I start and I stop right here, that's 0 radians. So what if I only go halfway around? I'm going 1 pi distance, right? If I go half of the circle, I'm going to go a half a pi, right? Or pi over 2, but I like to say it as a half a pi. Okay, it's pi, it's a half a pi. And then if I go 3/4 of the way around the circle, how far is it? It's 1.5 pi. Right? 1.5 pi. Or some people like to say it as 3/2 pi. Or 3 pi over 2. Okay? The number means something. It's how many that you have when you went all the way across. Okay? All right, so let's split this up even more. What if I go half of a half here? Well, it's 1/4 of a pi, right? So this is 1/4 of a pi, or this distance from here, starting here and ending here, is 1/4 of a pi in length. Or it's roughly about 0.75 of a radian, right? 3/4 of a pi. So it's 3/4 of a radian. So look at, that's about 3/4. That's a whole pi. That's a whole radian. 3/4 of a radian, 1 radian. Okay. All right, well, let's keep on going. So if this is 1 pi over 4, this one is 2 pi over 4. If this one's 3 pi over 4, this one's 4 pi over 4, this one's 5 pi over 4, this one's 6 pi over 4, this one's 7 pi over 4, and then this one's 8 pi over 4. So we're back to where we started. Make sense? Okay, so those are all the fourths on the unit circle. What about all those thirds and those sixths? Okay, so if we take this whole thing, it's kind of like a really big pizza. So you know how you slice a pizza diagonally through the center?
Squares.
Squares. Squares are, if you're going to Sal's, it's all squares. Yeah, squares are good too. So if I slice it into 6, if I do 6 slices, okay? If I do 6 slices, I'm going to end up doing something like around, like right around here and here, right? Okay, how far is each one of these? Like, how far is this? Pi over 6. Where did that come from? 1/3 of a pi over 2. So pi over 2 times 1/3 is 1/6. Okay, what's another way to look at it? 1/6 of a whole pi. Okay, so when we look at these are going to have the markings for the pi over 3. So here we go. So this is one of those pi over 6s. Okay, this is two of those pi over 6s. This is 3 pi over 6s. This is 4 pi over 6. 5 pi over 6. 6 pi over 6. See where I'm going? You just count. That's all it is. Okay? 7 pi over 6. 8 pi over 6. 9 pi over 6. 10 pi over 6. 11 pi over 6. And we're back to 12 pi over 6. Okay? But then some of these can be simplified, right? So which ones can be simplified? 2 pi over 6, that's a pi over 3. Or we say 1/3 of a pi. That's 2 pi over 3. So look at what's going on here. 1/3 pi, 2/3 pi, 3/3 pi. 4/3 pi, 5/3 pi, 6/3 pi. So if you are used to having memorized that unit circle, okay, memorize no more. Because on the AP exam, you're going to have to be able to figure out any one of these things at any given time, and you don't have time to go back and draw the whole doggone thing to figure out where something goes. You have to just pluck it out where you need it. Now, each one of these buggers has special coordinates, don't they? They got like the 1/2 and the square roots of 3s over 2 and the square roots of 2 over 2s. I wonder where those things come from. Where does that all come from? You know what I mean? Anybody remember this offhand? Pi over 6, what is it? That sounds about right.
Yeah.
It's a square root of 3 over 2, and it's got a 1/2 in it, and it's like a big squirrel them all together. Okay. All right, so what do I need you to do? I need you to know where it comes from so you know why it is what it is, because that's how this works. So,
Really hold your arm straight and then like use your. There's some shape to it.
there's. So, pi over 6 is right here. This has got one of those magic values, okay? And remember, what we're talking about here is pi over 6 radians. Radians is a distance that's wrapping around the circle starting at this point. That's what it is. It's a distance around the circle, okay? So, what are the coordinates of this point and why are they what they are? That's what I want to know. They come from the triangle, so let's make a triangle, okay? So oftentimes when we don't know something, we just make something up. Well, we generate something, okay? So I spy a triangle. Any angle measures that we know about this aside from the 90? 30. This is actually a 30, 60 degree right triangle. Okay, so this is the 30, this is the 60. Okay, so do we know anything else about the triangle? Hypotenuse is 1. 1 radian. Okay. All right, so where do the numbers come from then? We only know one of the sides. We don't know the other two sides. But we do know the angle. I know, because in geometry class, your geometry taught you that this side is always 1/2 the length of this side. And then this side is always the square root of 3 times the shortest side. Remember that? Why? Well, I don't know. Where does a 30-60 degree triangle come up? Well, let me show you. So there's an equilateral triangle. Okay? Equilateral triangle. And let's just make each side be 1 unit. Okay? Equilateral. What are the angles on an equilateral? They're all 60. Okay? So we'll put a 60 here, and we know the other ones are 60 as well. Okay. So if I take an equilateral triangle, which is a really cool shape, by the way. There's a lot of neat things about it. If I've split it in half, okay, and I only look at one of the halves, let's just look at the one on the left, okay? What kind of triangle is that? It's a 30, 60, 90, okay? So look at this. If this whole side was 1, you learn that a perpendicular, okay, bisector, okay, of the triangle splits these into 2s. So these are both a half, right? So what I see is, I see 1 for this side, 1/2 for this side. The only thing is we don't know what this side is. How do we figure out that side? We borrow a little bit of Pythagoras, okay? So Pythagorean Theorem says, let's just throw an h on this. 1/2 squared plus h squared is equal to 1 squared. Right? That's what Pythagoras would say. So 1/2 squared is 1/4 plus h squared is equal to 1. Therefore, h squared is equal to 3/4. Take the square root of both sides. And we get the square root of 3/4, which you learn to be the square root of 3 over 2. Because you can take the square root of the top and the square root of the bottom. Okay? So therefore, this length right here is the square root of 3 over 2. Voila, that's where the numbers come from. So now I'm just going to take that triangle, tilt it, put it here, and we recognize that this distance is the square root of 3 over 2. This distance is 1, and my coordinates there are 1 square root of 3 over 2 comma 1/2. Okay, that make sense? Now you don't have to say, geez, I don't know, I don't remember where it is. You know where it comes from. You can make it happen anytime. That's how we do things. Memorizing very little. You just start to just generate it as you need it. Okay, that helps to get this one over here, right? Because this one over here is just another 30-60, but it's faced the other way. And then this one's faced the other way, and then this one's faced the other way. So those 4 all have those same coordinates, but either positives or negatives based upon where they are in the quadrants. Okay, so far so good. Okay, now I need to know the pi over 3. So pi over 3 is over here. What are the coordinates on the pi over 3? Okay, I'll go along with that. Why is that? It's the same exact triangle, but we just flipped it. So this bugger just comes down here. And now we've got our 60, 30, 90. And then those are the numbers there. And that's why they are. So now we got these 4. And we're just about home. Okay? The last one is the pi over 4, or any of those fourths. So this guy right here, pi over 4, what are the coordinates on that guy? Square root of 2 over 2. Both square root of 2 over 2? Anybody else think that? Okay. So let me just see. If we draw our triangle, okay. So here's my triangle. Can't see it so good. So there's my triangle. Anything special about that triangle? Is it half a square? It's half a square. So this is a 45-degree angle, which means it's 45, 45, 90. This one is 1, so that means both of these have to be the same. This x and this y have to be the same number, because it's half of a square. So where does the square root of 2 over 2 come from? You know, I'm kind of just tired of telling you guys everything. Pythagorean Theorem? Okay. So here's a square and there's half a square, right? What's 1 in this picture? What's 1? The diagonal is 1. Okay? See this? Because it's really, there's your square. So this one is 1. And what are we out to find? This one and this one. I'm going to put x on there for both of them because they're both the same number. So now I'm going to use a little Pythagorean theorem. X squared plus x squared is equal to 1, which means 2x squared is equal to 1, which means x squared is equal to a half, which means x is equal to plus minus the square root of 1/2. And where do we get the square root of 2 over 2 out of this one? Rationalize the denominator. So how do we rationalize the denominator? We have 1 over the square root of 2, right? Because that's what this becomes. And you learn this little trick. You say, oh, if I multiply the top and the bottom by the square root of 2 over 2, then the square root of 2 times 1, that's equal to the square root of 2. And the square root of 2 times the square root of 2 is the square root of 4, and the square root of 4 is 2, so this is the answer. That means both of these are the square root of 2 over 2. So now that gets us all of them. Why? I got a question for you. You get this for an answer, and the teacher says, well, that's not in simplified form, right? You can't have any radicals in the denominator. Okay? So you simplify it, and then it looks like this. Now, I don't know about you, but when you simplify things, aren't they supposed to look nicer? Doesn't this look nicer than that? Why do we rationalize anyway? Seems kind of silly. I know why. Because you're not supposed to have a radical in the denominator. Why not? You ever think about that? You do it because you're told to do it. Right? But why do you do it? Who came up with that in the first place? Come after that guy. You know where it came from? Let me explain. Years ago, before calculators, where'd my moonwalk? Before calculators, we get an answer like this. We get an answer of 1 over the square root of 2. Okay? 1 over the square root of 2. Okay, I need that as a decimal. Can you just, no calculator, can you figure that out for me real quick? You say, oh yeah, no problem. I'm going to take 1 and I'm going to divide it by the square root of 2. Okay, it goes in there really nice. Okay, well that's no good. So I can't do that, but okay, I need an estimate. Just temporarily, give me a square root of 2 over, give me a square root of 2. What is the square root of 2? 1 point, give me a, keep going. 213,552. Because I wanted a pretty accurate answer. Okay? So I'm going to divide. How many times does 1.4142135 go into 1? Okay, well, I got to put a bunch of zeros here, right? Okay, and I should probably move the decimal places. Remember you learned that? Move these over here. And then 1, 4, so I'm going to multiply 9, 8 maybe. Then I'm going to get my answer, right? Okay. And I don't know, maybe 0.0771, something like that. Okay? Well, that seems kind of hard to do. So what these guys came up with is they said, you know, if we rationalize this puppy, all we have to do is say if this is the same as the square root of 2 over 2, and I say, get me a decimal number for that. Well, you're going to say it's 1.41422135, and we're going to divide it by 2. Better? Sure, look at this. That's going to go in there. What do I got? 1, 4. I got 0.7. 7. I dropped 7, 0, 1, 4, 7, 0, 7, 1. So all my numbers were wrong there. Okay? Look at that. That took like a couple of seconds to do. The only reason why you're asked to rationalize the denominator now is because people 300 years ago didn't have a calculator. And it was easier to divide a number by a radical by rationalizing it and then dividing the radical by an integer. That's the only reason why. But we still do it to this day. Okay? In this class, you do not have to rationalize any denominator. The AP test might have you do it. Okay, so now, I still don't know where the squiggly line comes from. Okay, still don't know where that comes from. So, I need to know what's the connection between that thing and this thing.
Your circle was better.
So, here's what we do. When we draw the sine wave, what we're really doing is we're looking at an axis that is theta. Theta is in radians, and it starts out at 0 radians, and it goes all the way around, okay, until it ends up at 2 pi radians, and then we can do one full circle. Okay? There's special magic points that occur here, and these are the points that are on the unit circle. So what I want you to imagine is I'm going to track at the t-table. My tracking is I'm going to go along 0. I'm going to go along around the circle where I'm going to start off at 0, and then every one of these special markers I'm going to put a mark down. So I've got pi over 2, then I've got pi, then I got 1.5 pi, and then I got 2 pi. This is me tracking around the circle one time. Okay? And if I'm supposed to graph the sine of the theta, then I'm tracking the y-coordinate. Tracking the y-coordinate of where I am on the circle. So here's 1 and here's -1 because I can never go above or below 1 or -1. Okay? So we plot some of them. So y-coordinates, okay? I need y-coordinates now. At 0, 0. Pi over 2, 1. Pi, 0. 1.5 pi, -1. 2 pi, back here. Okay? So now those are the 5 main points. But if we look at all the rest of them, if we say, what about pi over 6 and pi over 3? What are they are? Remember pi over 6? What is the sine of pi over 6? It's 1/2. So it scoots up all the way to 1/2 right here. So right here, we're marking it off. It's that height. Then as we plot pi over 4, pi over 6, what happens is it jumps up even higher. And so what happens is it kind of forms this little arc. That's why it's not a circle. You know, there's a sine wave in that. It's not a circle that just goes up and down like this. Then what's really cool is once we hit our maximum and we move down through each of the special markers that we just set up here, it's the same values, but they're just reflected. And so that's where we get this graph. And then it just continues. Then it's the y-coordinate. Where are we on the y-axis? We go all the way down to -1, and then we come back up to 0. So this is why this is why the graph looks like it does. Now wait a second. Does it stop there? Okay. How do we justify the fact that this actually goes on forever? You can keep on going around the circle. Okay? Because you can keep on going around the circle, that's how it keeps on going this way. And then you can even go backwards around the circle, and that's where we get it going to the left and to the right. So that's why this is continuous. It goes on and on and on and on and on. Make sense? So this is the graph of the sine wave. What does the graph of the cosine wave look like? Say it again. It's shifted to the left by 1/2 pi. So y is equal to the cosine of theta. So cosine values, right at 0, what's a cosine? It's an x value. It's 1. Okay? Then it's the same exact graph. Okay? So that's why it's going to look like this. And that's why the cosine looks like the way it does. Make sense? Okay, here's what I'm going to be needing from you, and we'll do a couple of practice rounds. Let me just throw a couple at you. This is a speed zone here. Okay. Sine of 5 pi over 6. Cosine of 2 pi over 3. Give me those two answers right now. No calculator. Turn away your unit circle. No looking. Okay, I'm going to show you a technique for doing it rather quickly. 5 pi over 6, first thing to do is to find out where it is. So it's totally legit to just draw a little circle so you can find out where it belongs. Okay, 5 pi over 6. 5 pi over 6 is 1 pi over 6 short of a 6 pi over 6. Right? That's a good insult for somebody if you really want to tell them. Like, if you fry short of a Happy Meal, yeah, you're about pi over 6 short of a full pie. Okay? 5 pi over 6, I want the sine value, so I'm going to go straight here. That's a half, just like that. Okay. Cosine of 2 pi over 3, that's 2/3 of the way to the pi, so I know I'm up at the top here. Cosine on this one, bring it straight down, that's a half. So both answers are a half, and you should be able to do that within a couple of seconds. That's what I'm going to need from you on the AP exam. And the cosine there is negative. Thank you. Okay. Good day. Be working on your homework because I want to take questions on that assignment today. Yes? No.